Hello, how's everybody doing today? I hope everybody's doing well this Tuesday afternoon and ready to investigate the fifth lab in Labflow, which is determination of the equilibrium constant. Up to this point, we tend to assume that the chemical reactions proceed until the end, until one of the reactants is gone, is consumed. We think many times that the reactions goes only in one direction, in the forward direction, and they have an end. However, there are many reactions that never ends. Those are called reversible reactions. They move in both directions, in the forward direction and in the reverse direction. And use double arrows to indicate that is a reversible reaction. So today's experiment is about understanding the equilibrium of these reversible reactions. These reactions that move in the forward and reverse direction at some point will reach an equilibrium. It's important for you to picture that because then you will understand what is going on. When the reaction reaches an equilibrium, what does that mean? It doesn't mean that the reaction reaches an end. No, it's a dynamic equilibrium. The reaction that moves forward has the same rate as the reaction that moves in the reverse direction. And that's why at equilibrium, this is an important concept. The concentration of the products and reactants will not change at equilibrium, but the reaction doesn't have an end. It's a dynamic state. Continuously, the reaction produces products, and the product produces reactant. And this dynamic state, when it reaches equilibrium, the concentrations of the product and the reactant is the same. But at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. This is just an important concept for the whole chapter of equilibrium. So what is the objective today, in today's experiment? Once you know what is equilibrium, we will study a reversible reaction, which is the reaction of ethanol and acetic acid. This is a reversible reaction. We will go over that reaction and we will determine the equilibrium constant. So the objective is basically be familiar with what is an equilibrium constant and do an experiment of reacting acetic acid with ethanol and calculate the equilibrium constant. So as we do each week, what I will going to do? I will start giving you a quick overview of the experiment. Then we will go over some learning check to make sure the problems, we can solve problems together. Many of the problems are similar of the ones that you are going to encounter in the pre-lab quiz. That's why they are there. And at the end of the workshop, what are we going to do? Go over the report. I want to make sure that you know how to do the calculations to complete your report. So let's get started by sharing the page of the experiment. Okay, as I always say, raise your hand. Don't think you are interrupting me. On the contrary, my objective is that you stop me as many times as you need so you can understand the concept and succeed in this and get the maximum amount of points to in your lab. Sorry, I got distracted with one text. It says, when we start a lab report in Labflow, do we have to complete it in one sitting? Not at all. No problem. I will answer any questions. So Alonso, you can actually start the report, save it, and actually when you are going to, let's say, oh, I cannot finish it, doesn't matter. Just save it. It will save automatically. And once you open it again, you will have the same data, and whatever you did is going to be there. Actually, the point is that they are not going to change you the data. So you will have always the same. And don't wait until the last minute. It's important. You can start today, continue tomorrow, definitely. So you are not going to lose anything. And many labs, like today is a very, not the concepts are a little bit, more tricky, but not that much compared to the time consuming that are the previous labs. This is really much less time consuming, but it's going to take time to explain and to go over the problems that you need to understand. Okay, so let's get started. So we are doing a determination of an equilibrium constant. So we talk about reversible reactions. Reversible reaction, I actually are expressed with this double arrow. When you see this double arrow, what does that mean? That it never ends. And those reversible reactions reach equilibrium. And some people think equilibrium, what does that mean? Well, it means two main concepts. The concentration, in this case, in this reaction that is shown here, A reacts with B, and the products are C and D in general, basically means that once the reaction reaches equilibrium, the concentration of the products and the reactants is not going to change, but the reaction is in a dynamic state because the rate of the forward reaction is the same as the rate of the reverse reaction. This is what's important and the concept. So it's a dynamic state. Let's review what they are saying here. So they are talking about what we just said, and we said that we use a double row. And what is without arrow? And what is interesting about these reversible reactions is that once they reach equilibrium, we have the expression of the equilibrium constant that relates the concentration of reactants and products. And here they are, this is the equilibrium constant. But what concentration are we going to plug in? C, D, A, B. We are going to plug in the concentration at equilibrium. And what is the equilibrium constant? Well, you see it here. Basically, is the equilibrium ratio of the products that are C and D. In this reaction, the products are C and D, to the reactants that are in the denominator, that are A and B, raised to the coefficient in the balance equation. What are the coefficients? This little a, this little b. So we don't forget to do that. Otherwise, you're going to calculate a wrong equilibrium constant. So we always have to have the balance equation and raised each element to the coefficient in the balanced equation. What else we need to know about equilibrium constant that is important? Well, we need to know that if you look at how the equilibrium constant is written, you have in the numerator up, you have C and D. In the denominator down, you have A and B. C and D, what is that? It's products. And A and B, what is that? It's reactants. So what is happening here is that if, let's say you have the same number, when you have a fraction, let's say you have a fraction, and you have in the numerator a number 2. And just to give you an example, and in the denominator a number 2 means the 2 divided 2 is 1. So we have an equilibrium constant of 1. What happens if we have an equilibrium constant, let's say an equilibrium constant, that the numerator is 4 and the denominator is 2. 4 divided by 2 is 2. What is the numerator for? Is the concentration of the products, of the products. So what I'm trying to conclude here is that we have to remember, if the equilibrium constant is higher than 1, what does that mean? Look at here, higher than 1, we got a number 2. The numerator is bigger than the denominator. The 4 is bigger than 2. That means the numerator represents the products. So if we have an equilibrium constant higher than 1, there are more products than reactants. And the equilibrium, one favors the products. So the equilibrium favors the product. And if the K is smaller than 1, favors the reactants. Any questions so far? This is what you are going to use all the time. Okay, so let's continue then. So now we said that we are going to calculate the equilibrium constant of this reaction. This is, don't pay attention at this reaction is an organic chemistry reaction. I taught organic chemistry, and if you continue studying chemistry, you will encounter this reaction. It's not our objective for you to know the details of this reaction, because this is an alcohol. This is ethanol. actually, you are going to see at the end, the last chapter is an introduction of organic chemistry. And you're going to learn that if it has an OH, it's an ethanol. If it has, and different, this is an ester. But for now, nobody wants you to learn that. But why they did this action here? Only because it's a reversible reaction and it's possible to calculate the equilibrium constant. But you are not supposed to know the detail. This is called a Fischer esterification. Basically, when alcohols and acids combine to form esters and water, because this is an ester and this is water, is called Fischer esterification. But all we expect from you is to recognize, okay, this is an alcohol and this is acetic acid. So you need to know that this is an acid. Acid you already seen in Chem 1, and you're going to see much more. What is the most important characteristic of an acid? I will write the formula of acetic acid in a different way. So basically, so you will know what is going on. This is acetic acid. I will give you in this way. Why? Only because I want you to see that this hydrogen is the acetic acid. So you will titrate this. This is the one that is going to leave. Acids release hydrogen. An acetic acid only has one proton to release. And that's what you are going to use in the titration with sodium hydroxide. But for now, all we are interested in, we are going to study this reaction of an alcohol, basically ethanol plus acetic acid, and we are going to obtain ethyl acetate and water. You should remember those names because then it's the only reaction. You will see that ethanol reacts with acetic acid and produces ethyl acetate and water. So you can remember those names, not even the formula you are asked to know, but you are asked to know that you have acetic acid and it has one proton to titrate. And also that the balanced equation is easy. See, you don't have coefficients here. You have a 1, you have a 1, you have a 1, and you have a 1. So this makes the calculation of here of the equilibrium constant much easier. Because we said, what do we said is the equilibrium constant? Is the ratio of the products to the reactants. So the products, we put it in the denominator, which is ethyl acetate, which is this one. So we do concentration of ethyl acetate here, times concentration of water, divided by concentration of ethanol, times concentration of the acetic acid. And we don't have to raise to any coefficient in the balanced equation because the coefficients are 1. Any questions so far? So we are going to study then this equation and calculate in the report the equilibrium constant of this reversible reaction. So basically here is talking about we are going to mix concentrated acetic acid and ethanol, and we have to add sulfuric acid that acts as a catalyst. is not included in the reaction because it's a catalyst. A catalyst only helps the reaction to be faster. It will reach equilibrium faster, but it's not consumed in the reaction. If we put 20 drops at the beginning, we are going to have the 20 drops at the end. It participates in the reaction, but is not consumed. Okay, so basically we are mixing that, and we are going to determine in this experiment the concentration of acetic acid using a titration with sodium hydroxide, 0.25 molar. So by titrate, we're going to do 3 titrations. We are going to start. Let's see what else it says here. Okay, how are we to do the titration? This is going to be a titration, an acid-base titration. So this one is the acetic acid. We are only going to titrate the acetic acid. You have seen in Chem 1 neutralization. So if you see, you have, this is acetic acid. That's the only one that's going to titrate the acid, but you are going to do it 3 times. You are going to calculate the initial concentration of acetic acid with a titration before the reaction starts. So basically, you mix the acetic acid and the ethanol, but you don't add the catalyst. And then you take 1 ml and you titrate with sodium hydroxide. And then you are going to do the reaction, and it takes a long time, an hour and a half. We are going to go over that, and then you wait until the reaction reached equilibrium, and you are going to titrate again, and you're going to obtain the concentration of acetic acid at equilibrium. So this is the second titration. And why did I say you have 3 titrations? Well, because when you start the reaction, you basically add 20 drops of sulfuric acid in order for the reaction to be faster. But we are interested only on the volume of sodium hydroxide needed to neutralize the acetic acid. So we need to do a blank, to prepare a blank with 20 drops of sulfuric acid, and then we'll take 1 ml and titrate that blank. And then we are going to subtract the volume of sodium hydroxide that the sulfuric acid consumes. We will go over each step, but this is basically a quick overview. So you have a general idea of what we are going to do. We are going to do 3 titrations, and we are going to obtain the initial concentration of acetic acid, the equilibrium concentration of acetic acid by using the volume that we subtract the volume of the one titration minus the volume of the blank, and we are going with that information will be enough to plug in the values and calculate the equilibrium constant of the whole reaction. Just by having the initial concentration of acetic acid and the equilibrium concentration of acetic acid, it's enough. Why? Because in this reaction, we are going to see a chart, but we mix equal amounts of ethanol, equal amount of mole. We add 0.5 moles of ethanol and 0.5 moles. We have the same number of moles of both. So I'll show you how to do the calculation. It's really not complicated. And with that information, you will be able to calculate the equilibrium constant. Before we continue, I wanted to show you how are we going to calculate, how we are going to do a titration. We said 3 titrations. Oh, let's explore a little bit about the titration. What is happening in the titration? This is acetic acid that reacts with sodium hydroxide. This is a neutralization. So you know from Chem 1 that when you have an acid that reacts with a base, what do we form? A salt and water. This is the neutralization. So how are we going to do the neutralization? We are going to add, we are going to take 1 ml of the acid. We're going to add an indicator, phenolphthalein, and we are going to titrate until it's pink, a very light pink. And how are we going to know? What are we looking for? We are looking for the molarity of the acid. That's all we want. The concentration of acetic acid. If we do it initially, we want the initial concentration of acetic acid. If we do it at the end, we want the equilibrium. But it's always the same kind of titration. So this is very easy. When you do the titration, basically, the volume is going, if you are in the lab, you are going to do it and have that volume. But because you're not in the lab, you are going to be, the data will be given to you. So how are you going to calculate the molarity of the acid? Going to be the volume of the sodium hydroxide times the molarity of the sodium hydroxide divided by the volume of the acid. Pay attention, we are going to see it when we do the report. You are going to, the volume of the acid, when you read the procedure in the write-up, you will see that you take 1 ml. So the volume of the acid is 1 ml. The molarity of the sodium hydroxide is given, is 0.25 molar. That's the concentration of the base that you use. And the volume will be given by the titration. And that's how you are going to calculate the concentration of the acid. But I don't want you to think that always you use this formula. In this case, because it's 1-to-1. If I'm titrating sulfuric acid, this is just for you to, sulfuric acid has 2 protons. So the formula will be different than this one. You will have to use the molar ratio. But that's okay, we don't have to worry about this. They are making our life easier. I just wanted to point out that if you are titrating sulfuric acid with sodium hydroxide, the formula will be different. Okay, any questions so far? Okay, so this is the equipment that you are using. All this setup basically is an organic chemistry setup. We don't have that for Chem 2, but they are showing you because they want to use this reaction in Labflow. So you will have to be familiar with this, a little bit with this setup. I use it only in the organic lab, but this is the only way to do the reaction, because what is happening is that we use the technique of refluxing. Refluxing, this is what the name of this, that uses a condenser. This is a condenser. And why do we need the condenser? Basically, the condenser captures the vapor. We have the reaction here, and captures the vapors and return them again to the liquid phase in the reaction mixture. So using this technique, why we need this technique? We can heat the reaction because the reaction takes 1 hour and a half until it reaches equilibrium. If we don't put the condenser, we are going to everything is going to evaporate because the organic solvents and compounds are sometimes volatile. So in order to be able to heat a reaction for an hour or an hour and a half, we need to use this technique of refluxing. So this is just in case a question arises, but you will learn this only if you do organic chemistry. You can watch the video. I think they are providing a video of this because sometimes questions in the pre-lab quiz, if you don't watch the video, there are some questions that you cannot answer. Okay, so we saw what is this, and then what else are they doing here? Okay, they're talking about a little bit about what we went over. Determination of initial concentration. So this is what we have seen. Basically, you mix 0.5 moles of acetic acid and 0.5 moles of ethanol in this round bottom flask that we saw. And then this is the initial. So we are going to transfer 1 ml of this mixture, and you can read all the details, add some DI water, add phenolphthalein, and then you will titrate with 0.25 molar of sodium hydroxide and record the volume of sodium hydroxide. And we said that we have to reach that pink color that doesn't disappear at least for 30 seconds. I think you did that in Chem 1. And we've already seen how to calculate from this formula the initial concentration of acetic acid. And then the part B, we need that volume of the blank. We already talked about that. We said that in order for the reaction to start, we add here, it says 20 drops of sulfuric acid. But we need a blank because we are not interested in how much sulfuric acid is going to, how much the sulfuric acid is going to consume of its sodium hydroxide. We are only interested in the volume of the sodium hydroxide needed to neutralize acetic acid. So then we need to do a blank. And while it is heating all that mixture, then you can do the blank. So basically, you titrate 1 ml of the blank with sodium hydroxide. And we don't have to go over because always is the same equation, this one. And in this case, we don't even have, for B, we don't have to do any equation. If for the blank, all we are interested is to record the volume of sodium hydroxide. We are not going to do any calculations because we are going to subtract the volume of sodium hydroxide needed to neutralize the blank. And then we are going to subtract. So for part B, basically, we are only interested in the volume, no calculation for part B. Why? Because when we get to part C, we are going to say, okay, we are going to say the volume in C of sodium hydroxide that I will use in the equation up here. Before I go to the equation, I will say the volume, and this volume is the volume that is reacting only with acetic acid. So this is part C. Once you already hit it and reach equilibrium, you are going to do a titration, but the volume that you are going to use in the equation that I show you is going to be the volume of the equilibrium that you got in part C minus the volume of the blank that you got in part B. Any questions so far? So this is the quick overview of this experiment. Once we have, so we are going to use this equation again for the final concentration or for the equilibrium concentration of this acetic acid, but the volume is going to be the volume that we take in part C minus the volume of the blank. This is, this is the volume, this volume, let me change the color, is the volume that goes here. And this is what we are going to calculate. Okay, and the last part, once you did all that work, you are going to calculate the equilibrium constant. Now, I will give you a quick overview, and then we are going to do the learning check. We will go over this again. But I want to show you that how are you going to calculate the equilibrium constant? So, you have the reaction that is ethanol, right? Okay, I wanted to do a better. Okay, ethanol plus acetic acid. Tell me if it comes. Writing with the mouse is not fun. It's going to give me ethyl acetate plus water, right? And we want to calculate the equilibrium constant. You know by now that you use those ICE charts. So initially, what do we have initially? We mix the same number of moles, right, of ethanol and acetic acid. And we have an initial concentration. And because we add the same number of moles, we know this concentration of both because we did the titration, initial titration. So this CI is known. I know the initial concentration of acetic acid. And because I mix the same number of moles, I have CI in both sides. And then what happens? ICE stands, C stands for change. I always add an H, but so what is the change? Once the reaction, once I add the sulfuric acid and I heat the reaction for an hour and a half, it reached equilibrium. What does that mean? In equilibrium, I lost this initial concentration of ethanol. I lost part is gone because it reacted the ethanol with the acetic acid to form the ester. So I actually heat it in order to produce some products. It doesn't go all the way to the end, but there is an equilibrium where the concentration at equilibrium do not change. So, and because it's the same concentration, the change is this. And whatever I lost here, I gain in the product. But I'm telling you something. In this equation, we have a 1 and a 1 and a 1 and a 1. Don't forget, if I have, let's say, a 2 in front of the water, it's not going to be x, it's going to be 2x. But in this reaction, we have 1, 1, 1, 1. Okay, then x. And then what happens at the equilibrium? At the equilibrium, I have Ci. At equilibrium, I add whatever I had before. Ci minus x, right? Ci minus x. And then in the product, I would say x and x. But what other information I have? I have this information. I have the equilibrium concentration of acetic acid, which is this, I have that number, and I will call it CF. So I did the titration, and I have two values. I have Ci, this is known, and I have CF. If I have those two values, I can calculate X. X is going to be what? Ci minus CF. And now I'm ready to do the equilibrium constant. The equilibrium constant is going to be, we said the ratio of the products, which is x squared. But what is x squared? X, we said, is Ci minus CF. And it's squared because it's x times x. Divided by what? By Ci squared. This is the first overview of how having the initial concentration, or let's say the equilibrium concentration, and the initial concentration of acetic acid, how you can calculate the equilibrium constant of this reaction. Any questions so far? This is your chance. Okay, so then I will go to some learning checks. I want to go over some exercises that you are going to encounter in the pre-lab quiz, some of them, obviously not all, and then we will go over on to the calculations of this of the report, but it's going to be very similar of what I have just explained on how you are going to calculate, not many calculations. So let's move to the learning check. Okay, so I have a few problems, and many of those problems are very similar, different numbers, but very similar to the ones that you are going to encounter in the lab quiz. So let's read this problem. It says, consider the reversible reaction of acetic acid with ethanol. When you react 8.65 molar acetic acid with 8.65 molar of ethanol, the equilibrium concentration of acetic acid is 3.29 molar. And they ask for the equilibrium concentration of ethyl acetate, which is the product. So you've seen it's very good to do those ICE charts. It helps a lot, and you have to have the balanced equation. You know that is 1-to-1. So this is very similar to what we have done in what I have just shown you. But let's go over. I do initial. What is the initial? Let's read again. You react 8.65 molar. So the initial is 8.45. And both use the same amount. And because at the beginning nothing is formed, I would do 0 and 0. Some people like to do a little line. Then, okay, so Kevin is asking, why is it 8. Oh, thank you, Kevin. It's not 8.45. You are right. I read it wrong. When you react 8.65. Thank you, Kevin. Somebody's paying attention. Awesome. So let me correct. Somebody's paying attention. I like that. Okay. So if Elena reads right, it says 8.65 and 8.65. Thank you, Kevin. And then what is the change? Obviously, minus x, and x and x. And then at the equilibrium, they are telling us that the equilibrium concentration of acetic acid equals 3.29. So they are giving us that number, 3.29. But we know that this is equals 8.65 minus x. This is given, and this is given, and this is given. Same is going to be with ethanol because it's the same amount. So we are going to say 3.29. And here we have x. So all we have to do, if we know from this equation, all we have to do is to solve for x. X is going to be 8.65 minus 3.29. Because they are asking for the concentration of equilibrium concentration of ethyl acetate, which is this, which is the X. So I have as an answer 5.36. Thank you, Alonso. Perfect. Yes. Awesome. That is the correct answer. Any questions so far on this problem? If you understand this, you're going to encounter similar problems in the pre-lab quiz. Okay, so then let's go over the second one. It says, let's read it carefully. using the same experiment that we did, that we just went over, determine the molarity. What does it say? Molality. No, it's molarity. Okay, this is a typo. Molarity. Okay, molarity of acetic acid. And they are saying 1 ml of the mixture of equimolar amounts of acetic acid and ethanol is titrated with this sodium hydroxide requiring this volume. So this is actually what we have seen. You know, volume of the acid times molarity of the acid equals volume of the base times molarity of the base. Same as we did before. Now, because we are calculating here the molarity of the acid, we have the volumes. 1 ml is the volume of the acid, and 25.25 mLs the volume of the base. So because both are in mLs, they're gonna cancel out, and we don't need to convert them into liters. You can, you're not gonna go wrong, it's just to make it easier. You can just, if you're calculating number of moles and you say volume times molarity, of course, yes. But in this case, the volumes cancel out and you don't have a problem. So basically, the molarity that is asked is going to be what? It's going to be 25.25 mLs times the concentration of the base, that is 0.1105 molar, divided by what? The volume of the acid, that is 1 ml. ml and ml cancel, and I obtain a concentration of acetic acid that is 2.79 molar. But this is the way you are going to do it. Any questions with this problem too? Okay, so let's go over the number 3. It says, consider the reversible dissolution of lead to chloride. And this is where you have to apply the concepts and some details about the equilibrium constant. It says, let's read it. Suppose you add 0.2412 grams of lead chloride to 50 mLs of water. They're giving you all the information in case you want to calculate some kind of concentration. When the solution reaches equilibrium, you find that the concentration of lead is 0.0159 and the concentration of chloride is 0.0318. And they ask for the equilibrium constant for the dissolution of lead chloride. If you watch the video, you will know the answer. I guess they are explaining that. This is a heterogeneous, I'm not pronouncing it right, heterogeneous reaction. Why heterogeneous? Because you will have a solid in equilibrium with the solution. And you actually need to have that solid there. But what is important is that in the equilibrium expression, the solids are not included in the equilibrium expression. So basically, we have, okay, they wrote here, actually. They wrote the reaction here. I don't need to write it again. Here is the reaction. Here is the reaction. So what would be the expression of the equilibrium concentration? We said products divided by reactants. But because solids are not included in the equilibrium expression, we will have to use only, it's going to be the concentration of lead times the concentration of chloride. What am I forgetting? Raised to the balanced equation coefficient. Don't forget that. We have a 2 here. So the chloride is raised to the second power. But if I want to calculate the concentration of this solid lead, they give us all this information, but we don't need to use it because when we have a heterogeneous equilibrium, we don't include the pure solids. Basically, pure solids and liquids are not included in the equilibrium equations. Remember that. That is important. Okay, so let's continue calculating this. And then now it's very easy. Concentration of lead, where is it? Here, 0.0159 times what? What is the concentration of chloride? 0.0, yes, thank you. 318 square. And I have a number that I got, 1.6. No, I got 0.0000, actually 4 zeros, and then 161. Yes, awesome, perfect. So this is a little tricky because the concentration of the solids and the pure liquids are not included in the equilibrium expression. This is a little trick. Thank you. Yes, perfect, because 1, 2, 3, 4, 5. Yes, Alonso, that's perfect. Yes. And now let's look at the last one that I have. This is all what we do encounter. You can also rewatch the video again if there is a part that. So this is between all the bad stuff of COVID. I mean, at least everything is recorded, and you can go over again if you need to. And then let's look at this one. They said, what is the equilibrium constant of the reaction? So we know that the solids are not included. So we have to look. Here we have an S, means solid. Here we have an S, means solid. So what will be the equilibrium equation? We start with the products and we say, okay, concentration of the product divided, and I look at the coefficient is 1, okay. And then on the other side, I don't include silver because there is an S. And then on the other side, I go silver nitrate, the concentration of silver nitrate, but there is a 2, so I need to raise to 2. Any questions so far about this? Let me see if there is another problem here. Oh, I had 2 more. I put a lot today. Okay, let's go over these 2 because actually the report part is actually simple because we went over most of it. So the report part is simple. So let's do it. Okay, it says, what is the expression for the equilibrium constant of the following reaction? Okay, so what is that I have to include and what is that I don't have to include? We said that pure solids are not included in the equilibrium constant. So this one, S, is not included, right? So what is the equilibrium constant expression? I look at the coefficients and I would say, okay, I start with the products, concentration of products, divided by concentration of reactant raised to the coefficient. Everybody agrees? Why we leave the carbon out? Okay. And the last one, yes, it's solid, perfect. Yes, exactly. Solids and pure liquids, they say they basically, this is for heterogeneous reactions. And the last one, I wanted to do it because there is a similar problem also there. It says, determine whether the forward or reverse reaction, either the forward or reverse reaction is favored in this equilibrium constant. We know that the equilibrium constant is a positive number. It's a value. It's a positive number. We have to look if the value is higher than 1 or is it higher than 1 or is it smaller than 1? What number is it's raised to the -5? So that means 0.000 exactly 1.8, 1, 2, 3, 4, 5 is smaller, exactly smaller than 1. And when it's smaller than 1, what does that mean? That there are more reactants is reverse. Perfect. Yes, I agree with this answer with you. And there are more reactants than products, and the equilibrium favors the reactants, which means is reverse. Any questions so far? So now we are going to jump into the report, which is simple. After you've done most of the work with me, it should be simple. Let's share the page of the report. Okay, here is what you are going to obtain. Calculations are really simple, actually, because you know you did 3 titrations, right? Okay, so what are they providing you? Here, they're saying the first information, it says for A, the volume of the first titration to calculate the initial concentrations. Okay. It doesn't write. Let me see. Okay, initial concentration. So we got the volume of sodium hydroxide, then the volume of the blank. And then at the end, after it reached equilibrium, they give us that. And they are making us the first question, A, that you have to complete. You're going to have different data, so you will have to do your own calculation. But how are you going to calculate in your case? You are going to use this equation that you're going to use. What should I write? Here, the volume of the base initially. Which one is mine? Initially, I'm doing A. I use this volume. So I will say 32.67 mLs. Now, the concentration is given is 0.25 molar. And what is the volume? You look at your procedure and you will see that you take a sample of 1 ml. When you do that calculation, you're going to obtain that the initial concentration of acetic acid is 8.17. Then, what else you have to do? You have the volume of the blank. That is given. You didn't do the titration. And then, in part C, what do you have to do? Same as we did before, but once the reaction reached equilibrium. But what is important here? That the volume that we use, is going to be, let me see if they give you that here. Okay, they give you the volume of the blank, and here they give you the volume when you titrate after it reached equilibrium. So the volume that you are going to use in the equation is going to be, in this case, minus 5.41 mLs. Why is that? Because that is the volume of sodium hydroxide that was consumed by the catalyst, that is sulfuric acid. We are not interested in that. We just want to know the concentration of acetic acid. And then it's easy. We use the same equation with this volume. This is going to be the volume of the acid. We use the same equation as we did before. And that's how you calculate okay. So this one, they ask you the volume of sodium hydroxide required to neutralize acetic acid. That is this, what we've seen. Now, from here equals, this is this. And then they will ask you for the final concentration. And then we do it again with the same as we did for the initial. And then they ask you for the calculation of the equilibrium constant. And that is what we have seen actually, but we can actually go, oh, let's look at my, we have the equation. Let's look at this. So we have the acetic acid. I don't want to write again everything, but the equilibrium equation. What do I need to write? I have here, they ask you to plug in all the number. Equilibrium or concentration of acetic acid. Perfect. Equilibrium concentration of ethanol or ethyl alcohol is going to be the same because we add we add the same number of moles. What is the equilibrium concentration of the product? We saw. How do I calculate the equilibrium concentration of the products? You remember that. In my case, it was. How do I obtain this? The 5.9 is going to be, remember I had 8.17 minus, you are going to have different values. What is 8.17? Let's go back. What is the initial concentration? A. Okay, have it in the other one. Let's look. Okay, here, see? It's going to be the initial concentration of acetic acid minus the equilibrium concentration of acetic acid. We saw that in our example in the ICE chart. And then once you have all these four, all you have to do is say, okay, now it's easy peasy. Concentration of the product square divided by the concentration of the reactants, obviously in equilibrium, and that's how I obtain that data. So the calculation, as you've seen, compared with what you have done for the previous two experiments, is much, much simpler. So I think this is a good stopping point. I will stop the recording and I will stay here to answer all the questions that you have. And thank you everybody for being here.